Okay, so I'm going to start our last chapter for the semester. So it's been a long semester, and I think we've learned a lot, hopefully, in terms of econometrics data analysis, not only in terms of the theory, but also on the practicalities of econometrics. And I'm hoping that anyone who's interested in looking beyond Econometrics 1, we have Microeconometrics offered next semester, and we have the Macroeconometrics or the time series econometrics offered every spring semester. So the even semester like we have right now. And for those of you, who will do data analysis in the future using regression analysis, I think hopefully a lot of the materials that you get in this lecture will be quite useful. Right. Another topic which I find very interesting and very useful, and I hope that a lot of students, particularly undergraduate students, will eventually use in the coming years, their independent studies or any kind of like research. They can use the limited dependent variable model. And so that's something that we're going to discuss today. All right, so I'm going to go through the overview of the limited dependent variable model. Limited dependent variable model is very, it's a very big literature, but I'm going to focus on just two methods. The first one is the binary dependent model, and then the next one is the multinomial model. Okay, so basically this is the overall overview of the lecture. We have the linear probability models, we have the Logit models, and we have the probit models. All right, so just to give you a brief overview on why we want to study using the limited dependent variable model. Many economic variables have restricted range of values. So we've seen continuous variable, we've seen discrete variable, we've seen categorical variable. So basically now we're going to focus not on the continuous variable, but we're going to focus on categorical variables or ordinal variables. Remember, the difference between categorical variable and ordinal variable is that ordinal variable has ranking. Now, let's focus on a particular categorical variable, which is a binary variable. So a binary variable takes only two values, okay? So for example, individual who is insured is going to get a value of 1, and another individual who is not insured is going to get a value of 0. Now, this is something that you should be familiar with in the sense that when you study dummy variable, you study a binary variable, okay? For example, a binary variable on female as a gender. So you input 1 if the individual or the respondent is a female, and then 0 if it's a male. Okay, now, many times the variable of interest could take more than two values. Okay, so in this case, we're not dealing with binary variable, but we're dealing with categorical variables with more than two categories. In this particular case, it's again the ownership of insurance. So instead of having information on whether an individual is insured or not, we have an information on the type of the insurance as well as whether the individual is not insured. In this particular case, individuals who is insured, they can have the national healthcare coverage. In Indonesia, we call it the JKN or the BPJS Kesehatan. An individual could also have private insurance, and I'm sure that many of you not only have BPJS Kesehatan, but many of you have private insurance as well. And then otherwise means that you have no insurance at all. And so these are basically the two variables that we're going to study today. So the first one is the binary variable, and then the second one is a categorical variable with more than two values. All right. So before I continue, any questions on the idea of a binary variable as well as multinomial model? Go ahead. All right, I guess I can continue. So I'm going to continue into the next one, which is the binary response model or the binary variable. Okay, so I'm going to start with the model specification first. So it's quite important for students to be able to understand how to write a binary response model. So in a binary response model, the interest lies primarily in the response probability. Okay, so we're interested in the response probability. The way that we write it is the following. Again, you have y, which is a binary variable with just two values, 1 or 0. And then we want to know the response probability. Okay, what's the probability that individual is insured, for example, conditional on some observables. So the observables include individual level characteristics, for example, or other aggregate characteristics that could affect the probability of y equals to 1. So we can say the probability of individual being insured, conditional on observable. If we're interested in looking at the probability of individual being unemployed, conditional on some characteristics. You're also probably interested in the probability of individual, say, contracting COVID-19 virus, conditional on observable. So those are several interesting analysis that you can think of using the binary response model. Okay, so again, we're interested in looking at the response probability. So the probability that y is equal to 1, conditional on some observable. Okay. So I gave you many examples. So I guess I'm gonna give you 1 minute to think about the type of analysis or the type of variable that you're interested in, the type of binary variable that you're interested in. And then, you know, we can think about the response probability from there. All right. So I'm going to give you a minute, and I'm going to randomly select an individual to mention what's an interesting binary variable that you want to investigate. So a minute from now, go ahead. Okay, anyone who wants to share a binary response model that they're interested in, or a binary variable that they'd like to analyze? Anyone? Okay, so I guess I can start. I have here Asoka. Asoka, do you have a suggestion on a binary dependent variable that you like to analyze? Go ahead.
I'm sorry, sir. I'm still thinking about it. I'm still trying to understand the material first.
Okay, I'm going to get back to you in about 30 seconds. I'm going to give the other an opportunity first. So Mazaya, can you give me an example on a binary variable that you're interested in?
For example, hello, sir, can you hear me?
Sure, yeah.
Okay.
So it's a categorical variable with just two values, 1 and 0. An example that we discussed is about whether or not an individual is insured. And another example would be whether or not an individual is employed or whether or not an individual is unemployed. So those are examples of binary dependent variable. Anything that you can think of?
What about retirement, sir?
Okay, so during the COVID-19 pandemic, a lot of firms actually offered their employee, a retirement package. So that's one thing that it's interesting to know. What's the probability of an individual taking a retirement package, an early retirement package, given or conditional on observable? Okay, so that's an example. Thank you. So I'm going to go back to Asoka. Asoka, can you give us an example?
Probably elections, maybe.
Okay. Can you be more specific into what kind of election that you're referring to?
Like an election where there's two candidates and like you want to know whether whether like people choose like candidate A or candidate B, maybe.
Okay, so I'm just thinking about basically the example is correct. So you have, say, for example, two candidates. And so basically you can represent that using a binary variable. So whether a candidate A is selected or not, but I'm just, thinking about the bigger picture. So suppose that you have a micro data with characteristics of individuals' voters. And then given the individual's voters, you also ask whether the individual voter voted for candidate A or candidate B, and then you want to know whether or not there is a difference in characteristics between those who voted for candidate A versus candidate B. Okay, so very good. So those are some additional examples of binary dependent variable that's interesting out there, and I'm sure that we have 40 students here in the class. I'm sure that there will be more examples of binary dependent variable. Okay, so given that we understand the response probability, so the probability that y is equal to 1 conditional on some observable, now we would like to model that response probability. So the first one is going to be the linear probability model. So many times the linear probability model is referred to as the LPM. So using LPM, we're, as the name suggests, we're going to model the probability function as a linear function. So the response probability, Py equals to 1 conditional on some observable, is just a linear function of the explanatory variable, okay? And so if we have x1 until xk, we can write the probability y equals to 1 is a linear function of x1, x2, x3, x4 until xk, okay? So basically the model says that the probability of success or the response probability, so the response probability could also be written as just the P of x for simplicity. So the probability of success or the response probability is going to be a linear function of the explanatory variable xj. So it's very simple. It's a linear function of the explanatory variables. However, although it's a simple model, it's a linear model, it's going to have some disadvantages. It's going to have some drawbacks. So that's something that we're also going to discuss in this particular lecture, the disadvantages as well as the drawbacks of using the linear probability model. Okay, but again, just to give you guys another emphasis on some of the definitions that we're going to use. So P of x, or the probability y equals to 1 conditional on x, is going to be referred to as the response probability, or the response probability or the probability of success, okay, conditional on some observable. So that's a linear probability model. So it's a model which suggests that the response probability or the probability of success is a linear function of all the explanatory variables in the model. Now, given that we have a linear function, then the marginal effects of a change in one of the explanatory variable xj is just going to be quite straightforward. Okay, so in particular, the marginal effects of a change in xj is just going to be beta j. Okay, so suppose that I have a very simple model. So the probability of success is just a linear function of beta 0, beta 1 x1, beta 2 x2 plus epsilon. Okay, so the marginal effect of a change in x1, for example, is just going to be beta 1. Okay, so again, this beta 1 is going to represent the predicted change in the probability of success when x1 changes by 1 unit. So, ceteris paribus, of course. So this is a, basically a general definition that, we learned some lectures ago, starting in lecture 2 and 3. So the marginal effect of a change in a particular variable on the probability of success. Okay, so before I continue, any questions on the linear probability model and then the marginal effects of a linear probability model? Go ahead. Okay, all right, so I'm going to continue to the next discussion. So how do we estimate the linear probability model? So given that it's a linear model, so it's a relatively straightforward for us to implement the, go ahead if you have a question. Okay, so again, given that it's a linear function, it's going to be quite straightforward, and then we can implement the OLS regression to estimate the beta ones. Okay, so basically we're interested in estimating beta hat j. So I'm going to give you an example. So the example will be a health and retirement study from Cameron and Trivedi book. So that's something that we're going to do in Stata later on. So the exercise is interested in looking at the relationship between income and purchase of private insurance. So although we're only interested in looking at the relationship between income and purchase of private insurance, of course, we're going to control for other observable characteristics or observable variables. Okay, definitely we're going to look back into the discussion, but before we do a linear probability model estimation in Stata, I'm just going to go through several issues that we will face when we're doing linear probability model. So the first issue with linear probability model is that the predicted probability can either be less than 0, more than 1, or they can be both less than 0 and more than 1 at the same time. And why is this problematic? Well, if you recall your statistics 2 course, you can remember that the definition of probability is between 0 and 1 inclusive. Okay, so there is no such thing as probability being negative and probability being larger than 1. Now, the biggest issue with the use of LPM is that the predicted probability is beyond the numbers which is allowed in the probability theory. So that's the major issue. So this is one particular example of the predicted probability given the model, and this is something that this is something that we're going to see in Stata later on. But I'm going to go into the second point. So in addition to the predicted probability being larger than 1 or lower than 0, the probability is also linearly related to the independent variables. So what does it mean? It means that the marginal effects is fixed. So the marginal effects of the change of a particular variable on the response probability is going to be the same regardless of the value of that variable. Okay, so for example, going back to the health and retirement study conducted, we're interested in looking at the effect of income on insurance ownership, private insurance ownership. So a linear probability model will say that whether the individual is rich or the individual is at the middle of the distribution or the individual is relatively poor, they will have the same marginal effect of income on the probability of having a private insurance. Now, that is a relatively strong assumption. In practice, we can say that, oh, the marginal effect of a change in income on the probability of having a private insurance is probably lower among the richest individuals in the data, but it's going to be relatively higher for individuals in the middle of the income distribution, as well as individuals in the lower end of the distribution. And so assuming that the marginal effects is fixed for all level of income is something that is quite hard to define. So that's the second issue with having a linear probability model. And then the third issue with having a linear probability model is that the conditional variance of y by design is going to be heteroscedastic. And why is it going to be heteroscedastic? Because the variance of y conditional on x is going to be a function of the explanatory variables. Okay, so and if you recall, if there is a relationship between the variance of y on the characteristic, observable characteristics, then that implies heteroscedasticity. So again, we're interested in looking at the estimate for beta j as well as the standard error of beta hat j. So heteroscedasticity is not going to bias the estimate of beta j. However, heteroscedasticity is going to bias the standard error, okay? The standard error of the estimate. So those are basically the main issues of using the linear probability model. And given the issues of linear probability model, scholars at that time mentioned, well, we need something else that is going to be useful in doing the estimation of a binary dependent variable, and that's something that we're going to discuss next. So basically, we need to find a function. It's not going to be a linear function as in the linear probability model. So the function at least will allow us to limit the response probability between 0 and 1 as mandated by the definition of probability and probability theory. And then there are two candidates that we're going to consider. So the first candidate is the logistic function, and the second candidate is going to be the standard normal CDF. Okay. All right. So before I move on into the discussion of the logistic function as well as the standard normal CDF, I'm going to open up the floor for questions. Go ahead.
Just to clarify, sir.
Yeah.
If LPM violates the homoscedasticity assumption, does that mean that it's not blue?
Yeah. Yes, definitely. So, so there are several properties, right, in blue estimator. So blue means best linear unbiased estimation. So yes, OLS, binary dependent under OLS is still a linear function. If we fulfill the zero conditional mean assumption, then we could get probably an unbiased estimate. However, the best property of blue may not be fulfilled because there is that the violation of the homoscedasticity assumption. Okay, cool. Any other response? Okay, good. So I guess we can continue into the next discussion, which is the Logit and the Probate model. So there are several stata exercises, but I'm not going to show you that right away. I want you to be able to understand what a Logit model is, what a Probate model is. And so you guys can make a comparison between the Logit model, the Probate model, and the linear probability model. Okay. All right, so I'm going to start with the Logit and the Probate model first before we continue. So there are going to be some notations that looks relatively advanced, but again, if you look closely, then it's actually not. So bear with me for several moments to make sure that you understand the notations as well as some particularities in each function. So the first one, again, we're interested in looking at the probability of success or the response probability. So the response probability is a general function G, and G consists of the explanatory variables. Remember, in the linear probability model, then the G function is just going to be a linear function. However, in this particular case, we're not going to elect for a linear function. So G is going to be a function taking on values strictly between 0 and 1. Okay. Again, it's going to take a value between 0 and 1. So there are two candidates, and we are going to discuss the first candidate, which is the Logit model. So in the Logit model, the particular G function that we're referring to is going to refer to as the logistic function. Okay, that's why we get the name Logit model, because it's based on a logistic function. So what is a logistic function? Again, we're not going to go through the nooks and crannies of a logistic function. So the logistic function is a ratio between the exponential value of z with 1 plus exponential value of z. So what is z here? Okay, so z is just a value. And if we go back to the previous slide here, so z is going to be the combination between the parameter and then the independent variable, so g of z. So it's going to be relatively more straightforward if we write it as a z instead of beta 0 plus beta 1 x1 plus beta 2 until beta k xk. All right. So again, this is the first thing that we need to address. In the linear probability model, the response probability could get higher than 1 or lower than 0. In the Logit model, then it's always going to be between 0 and 1 for all value of z. In the next graph, we'll see that. So this is a CDF function. So what is a CDF? CDF is a cumulative distribution function for a standard logistic random variable. Okay, and again, the value is always between 0 and 1, and this is the depiction. Okay, so you can imagine that the horizontal axis is going to be z. Okay, and then the vertical axis is going to be the g of z. In this case, the g of z is the cumulative distribution function. And the good thing is that it's always between 0 and it's always going to be between 1. Another interesting observation that you can find is that the model is no longer linear. Okay, so as you can see, the slope that you have right here is relatively different with the slope that you'll have right here, and then definitely the slope that you have right here. And so in this particular case, the model is no longer linear. It's a non-linear model. So the second model that we're interested in is going to be the Probate model. So what's different between the Logit model and the Probate model? Well, the difference is on the function G. In the Logit model, the function G is a logistic function. However, in the Probate model, the G function is going to be the standard normal CDF. What's a CDF? Again, a CDF is a cumulative distribution function. So if you recall the discussion in statistics 1 as well as in statistics 2, you can remember that you have the probability distribution function or the PDF, and you can also have the cumulative distribution function. Now, the good thing about a cumulative distribution function is that the value is always going to be between 0 and 1. Now, you'll see that there is a formula here, and I'm not going to ask you to memorize the formula, but again, I just want you to make a distinction between a probability distribution function and then cumulative distribution function and how those two differ, okay? Now, I'm gonna just briefly provide you with a refresh. So if you remember, there is this bell curve associated with a normal distribution. So this bell curve is not a CDF. This bell curve is called the probability distribution function. Okay. So what is a CDF? Well, a CDF is going to be the area of the graph from negative infinity to Z. Okay, so if you look at here, suppose that this is a particular value Z. So the area between the negative infinity until Z, sorry, that's not infinity, that's an 8. So let me revise that. So the difference with the area between negative infinity and Z is going to be the cumulative distribution function up to point Z. Okay, and then the cumulative distribution function itself, it's going to look like the following. So suppose that this is Z, then a cumulative distribution function will look like that. So it's going to be around here is 0, and then here is going to be 1. Okay, so the value is always going to be between 0 and 1. So basically that's going to be the Probate model. It relies on a standard normal cumulative distribution function. Okay, any questions before I go and discuss latent variable model? Go ahead. Okay, good. All right, so if there's no question on Logit and Probate, we'll go into the latent variable model. Just to summarize, again, why do we need a Logit model and why do we need a Probate model? We need a Logit and we need a Probate model because we want to identify or accommodate the non-linearities. And we also want to make sure that the response probability or the predicted response probability is always going to be between 0 and 1. All right, so given that setup in mind, let's go and discuss the latent variable model. So let y star be a non-observed or latent variable. So the latent variable is something that we do not observe. So suppose, oh, I want to get myself insured, and then there is some value in that latent variable such that if the value exceeds 0, then I'm going to get myself insured, for example. But then if the value is between or equal, if it's lower than or equal to 0, then we do not get insured. That's a particular example. Now, economists likes to use the latent variable model because it's going to tie quite nicely with the probit model. And we also like to use a normal distribution assumption. Okay, so several remarks before we discuss several particularities. First one is that the unobservable E is going to be independent of X. In the Logit model, we assume E has the standard logistic distribution. And then in the probit model, we're going to assume that E has a normal distribution. Okay, so what's the thing about a normal distribution? Recall that G is a cumulative distribution function. Okay, so a property that is relatively common, and it's actually a very nice property of standard normal distribution, is that if you have 1 minus the cumulative distribution of negative z, it's just going to be the g of z. Okay, and why is this particular function possible? This particular function is possible because we have symmetry in the normal distribution. Okay, so I'm going to go back to the scratch node that we have earlier. Again, we want to show that 1 minus g of negative z is going to be g of z. Okay, now I'm going to first draw you the PDF. Okay, again, this is the probability distribution function, and suppose that this is negative z. Okay, and so here in this case, this is going to be the cumulative distribution function up until negative z. Okay, and if you notice, this shaded area in orange is going to be 1 minus the cumulative distribution of negative z. And why is that? Well, it's because that the area of all the area under the graphic in total must be 1. Why? Because that's the properties of probability. And so the orange shaded line, the orange shaded area is just going to be 1 minus whatever is the area of G until negative Z. And the nice thing is that you can draw a relatively same graph. Again, I cannot make it as simple as possible. And here, this is going to be so here. So the orange shaded line in this particular case is going to be the cumulative distribution function up until point Z. Okay, and then due to the symmetry, Z is going to be negative Z is going to be the absolute value of negative Z. And so in this particular case, G of Z is just going to be 1 minus G of minus Z. Something that you need to remember if you're using a normal distribution. Okay, any question for this particular property of normal distribution before I continue? Okay, all right, so I guess we can continue. So economists like the normality assumption for E. Okay, so again, that is why the probit model is going to be more popular in econometrics. So when you ask whether the results from Logit model and probit model will be the same, the answer is no. So the results from estimation using Logit and using probit is going to yield you different results, although not significantly. Okay. Now, in the old days, the probit model is computationally heavy. So it's going to take some time for the computer to run a probit model. However, in computer nowadays, so if you have, the latest generation of Intel chips, or if you have the latest iteration of M1 chip, I don't think that's going to matter a lot. It's going to be relatively quick, again, depending on the number of variables as well as the number of observations that you use. But in general, if you compare the Logit model and the probit model is going to run heavier. But again, given the modern computer, I think it's not going to matter that much. Okay. All right. So recall the latent model. So in the latent model, you have y star is going to be equal to, say, beta 0 plus beta x, for example. So let me just, for consistency, I'm going to write this as x beta. Okay. And then the probability of y equals to 1 if the latent model is strictly positive. Okay. And so, sorry, this is plus e. So let me revise. Plus e is going to be larger than 0. And so if you just do some relatively minor arrangement, you have e larger than negative beta 0 minus x beta, or you can make this into a bracket and then you have plus inside it. So the probability of e larger than negative beta 0 plus x beta, so you can have this as z as an analog. So the probability that e is larger than some negative z, okay, is going to be 1 minus g of negative z, and 1 minus g of negative z is just g of z itself, or the z is beta 0 plus x beta. So the primary goal is to explain the effects of a change in the explanatory variable xj on the response probability or the probability of success. Okay, so that's going to be the goal that we have for the next few lines. Okay, any questions before I go on? Okay, cool. So now, given that we have a bit of understanding on the modeling side of the Logit and then the probit model, we're going to discuss about the direction on the effect of xj on the response probability. Okay, so basically the direction of the effect of xj on the response probability is always going to be the same. However, the latent variable y star rarely has a well-defined unit of measurement. So the magnitude of h beta j are not going to be especially meaningful. So what does it mean? So when you do a Logit regression, or when you do a probit regression, and then you have the regression results, now the estimated coefficients from the Logit and the probit regressions are not going to be meaningful. So you're not going to be able to use it right away, and you need some further calculation using particular methods, which is something that we're going to discuss before you can actually do some interpretation. Okay, so again, you may not be able to do some interpretation directly on the estimated coefficients for Logit and probit. You need to do some follow-up calculations. Okay, well, what kind of follow-up calculations that we need to be able to interpret the regression results? Okay, well, this is something that we're going to discuss. Again, what we're interested in is looking at the partial effect of px as a change in xj by 1 unit. Okay, so in this particular case, it's not just beta j as we have in the linear probability model. Okay, so this is not going to be the case. So the marginal effect of a unit change in xj on the response probability is going to be a bit more involved in this case. It's going to be nonlinear, and we'll see why that is the case. Okay. Well, again, as you know, we have the p of x, and the p of x is a function, CDF function on beta 0 plus x beta. Okay, and then you want to take a partial effect of the response probability with respect to a particular explanatory variable xj. So the first thing that you're going to do is you're going to have the first derivative of px with respect to the CDF function. Now, the first derivative of a CDF function is going to be a PDF function. Okay, so PDF here is denoted with little g. So big G is for the cumulative distribution function. Little g is for the probability distribution function. If you cannot recall directly, that's okay. You need to revisit statistics 2 course. And in statistics 2 course, you'll see that CDF is an integration of PDF up to a particular point. And then PDF is going to be the first derivative of the CDF. So that's something that you need to recall. And then after you take the first derivative of the response probability with respect to the CDF, and then it's the first derivative of the CDF on the explanatory variable xj. And so that is just going to be beta j. Okay, so when you do your logit and probit regressions, it's still gonna be meaningful in the sense that it's gonna provide you with the direction. So whether or not beta j is positive or beta j is negative, no more than that. So when you do want to do the interpretation, then you need to you need to also take into account that there is non-linearities in the model, and that non-linearities is going to be represented by this particular scale factor. So how do we calculate the scale factor? And that's something that we're going to discuss in the next few slides. Okay. All right. Any questions before I continue? Okay, good. All right. So again, let's go into the discussion on the marginal effects of a change in explanatory variable xj on the response probability. Okay, so again, we're interested in this particular discussion. How big is the change in response probability if the explanatory variable xj changes by 1 unit? So the big question is, what kind of variable xj that we can analyze? Well, first of all, can you do a binary explanatory variable? So the right-hand side, the xj, is a binary variable 0 and 1. The answer is yes. So can you have a nonlinear variable xj? So for example, can we have x1 square? Can we have log x2? The answer is yes. It's possible for us to have squared variable to the power of 3, variable to the power of 4, or any polynomial of degree n. And we could also have a log transform variables. Okay, so in this particular case, if we are interested in looking at the partial effect or the marginal effect of x1, it's going to be the partial effect of x1 on px, and this is the scale factor that we discussed in the previous slide. And this is going to be the first derivative of the CDF function with respect to x1. So the first derivative of beta 1 x1 is just beta 1, And the first derivative of beta 2 x1 square is going to be 2 beta 2 x1. And if we're interested in looking at the change of x2 on the response probability, we have the scale factor, okay, something that we discussed in the previous slide. And we also have the first derivative of the CDF with respect to x2. So the first derivative of the CDF with respect to log x2 is just 1 over x2. And so we have this. All right, so this is the Logit and the Probate model. Okay, and then the marginal effect of or a partial effect for a different right-hand side or explanatory variable. You can have a continuous variable, you can have a binary variable, you can have a log transform variable, and you can have a quadratic variable. Okay, any questions before we go and discuss the estimation? Okay. All right. I'm going to continue into the discussion of discussion of the estimation. So let's go into that discussion right now. So again, this is relatively technical, and I don't want you to spend a lot of time on the issue of estimation, but I think this is going to provide you with a brief knowledge on the estimation of a non-linear model. So you've seen estimation of OLS, which is relatively straightforward. And then you can use the matrix to make it even concise, if I say so. But here for the nonlinear model, estimation is going to be relatively complex. And so basically an OLS or a weighted least square is not going to be applicable. So for nonlinear models, then maximum likelihood estimation, or usually people call it just the maximum likelihood, is an estimator that we can use for nonlinear models. Okay, so if you do not know what a maximum likelihood estimation or a maximum likelihood estimator, please refer back to your statistics 2 course, and then in that statistics 2 course, we'll be able to learn about maximum likelihood. Okay, so suppose that we have a random sample and the size of the random sample is n. We can write the density of y into the following. So the density of y conditional on the information that we have, and then the parameters beta that we're going to estimate is going to be the following. So it's the cumulative distribution function g. It could be the logistic function. It could be the normal standard normal function, depending on whether or not you do a logit or you do a probit. To the power of y is going to be 1 if you if the response is 1, or you have 1 minus g the CDF to the power of 1 minus y, and again y is going to be 0 in this case. So the log likelihood function, if you take the log transform of the likelihood function, you'll get the following. You have the yi log the CDF, and then 1 minus y log 1 minus the CDF. Okay, again, g is going to be strictly between 0 and 1, and the log likelihood is well defined for all values of beta. Okay, now you have that for each individual I, and then if you sum it, you'll have the log likelihood function, which is the sum of all individual log likelihood, and then you're going to do estimation given this particular function. So the idea is that you want to have a set of beta hat j such that you maximize the log likelihood function. That's why you call it the maximum likelihood, because you're looking for an estimator that maximizes the log likelihood function. Okay, so again, if you use a logistic function, CDF of the logistic function, then you're using the Logit model. And if you're using the CDF, the normal CDF, it's going to be the probit estimator. Now, if you fulfill the general conditions, the general assumptions, then the maximum likelihood is going to provide you with a consistent estimator. So if you think about the OLS, you're thinking about a non-biased estimator. In MLE, it's no longer bias unbiased. It's going to be consistent versus not consistent. So basically, the consistent is going to be the analog of unbiasedness. It's going to be asymptotically normal and then asymptotically efficient. So what does it mean to be asymptotically? So it's going to be asymptotically efficient, means that you have more observation in your data. Okay, so that's going to be on the estimation of the logit and probit. And again, this is something that we touched upon a few slides back. After you do the logit and after you do the probit estimation, you do not necessarily interpret the estimated coefficients. Why? Because it doesn't have any meaning to themselves other than the direction, positive or negative. Okay. And if you want to do some interpretation, then you'll have to look more into the logit and the probit estimates discussion that we're going to go through. But before that, let me open up the floor again just to make sure whether or not you have questions. All right, cool. So let's go into the logit and the probit estimates. Again, we're going to go through this in Stata for a moment, but I want to go through all the important discussions first. Okay, so we have the predicted probability. Again, you know, when we talked about, you know, whether an individuals want to get retired or not, then we want to predict what's the probability of that particular individual take the retirement package conditional on observable. That's something that, you know, we can definitely analyze, or, you know, given a particular voter's characteristics, what's the probability that he or she will pick a particular candidate, say candidate A. So that's a predicted probability. And again, we want to use the logistic model, the logit and the probit model in such a way that the predicted probability is always going to be between 0 and 1. Okay. All right. So this is a depiction of the OLS, or the linear probability model, and the logit model. Okay. So basically, as you can see, the logit model, the predicted probability of the logit model is always going to be between 0 and 1. However, for the linear probability model, it could exceed 1. So what's the probability of individual with income of $100,000, for example, monthly income of $1,000, then the probability of having private insurance ownership is going to be about 1.5. It doesn't make sense to have a probability of 1.5. Okay, because you need to always have probability between 0 and 1. And you can also distinguish between the logit and the probit relative to the LPM. So the blue line is the logit, and then the dotted green line is the probit. As you can see, there's not much to separate between logit and probit. However, you can see stark difference between the logit, probit, and the linear probability model. So what's the message here? So the message here is that if you want to make sure that the predicted probability is always going to be between 0 and 1, we should use the Logit and the probit model. Another interesting thing is that in the linear probability model, we're going to assume constant marginal effect or a constant partial effects. However, for the Logit and probit, you can see that the effect of a change of a explanatory variable xj on the response probability is not going to be linear. And this makes sense. For example, suppose that we have a distribution of income. So first we look at relatively rich individuals. For the relatively rich individuals, additional change in income will not have as high effect on the probability of having a private insurance. Why? Because on average, these people already have it. However, if we look people in the middle of the distribution, then say a unit change in the income, it's going to have a larger effect on the change in the probability of having a private insurance. Why? Because the likelihood that they have private insurance in the beginning is not relatively high. So that's the main difference between OLS and Logit and probit. And of course, there's that issue of heteroscedasticity by design if you're using the OLS. Okay, so recall that when we do the partial effect of a change in P of X on xj with respect to xj, you have this G beta 0 x beta multiplied by beta j. Okay, now the question is, how do we estimate this particular scale factor or the PDF of beta 0 plus x beta? Well, there are several ways in which we can estimate G. Okay, so the first thing that we're going to do is say we can use the means, we can use the medians, we can use the minimums and the maximums of the explanatory variables in the data. Okay, so it's going to be data driven. Okay, we can use the minimum, we can use the maximum, or we can use the means and medians. Okay, so the first one is the partial effects of the average. Some people say that it's the marginal effect of the average. So you can use the partial or you can use the marginal, it doesn't really matter. So what does it mean? Okay, suppose that we want to evaluate the effect of, say, some particular variable. We need to first calculate the little g function. So in this case, the little g function is going to be a function of the mean or the average. So that's why they call it the partial effect of the average, okay? Because we're taking the average first. So we're going to obtain the partial effect of xj for the average person in the sample, okay? And we call this the partial effect of the average. What are the problems? Well, first, what if the explanatory variable is a discrete variable? So suppose that you have marital status, whether you're married or not. What does it mean to be married equals to 0.600, for example? Or for example, if it's a gender, and in particular, it's a female. So female equals to 1, 0 otherwise. And suppose that you have a average of, say, 0.4. What does it mean? So for some discrete variable, it doesn't really make sense for us to do marginal effects of the average. It's fine if you have all the continuous variable. However, in a lot of settings, particularly if you're using microdata, then more likely you're going to use discrete variables in the analysis. And so given that you're going to be using a lot of discrete variables, then it's going to be relatively difficult to interpret using the marginal effects of the average. And so what is the alternative? Well, the alternative is to use what's called the average partial effect or the average marginal effect. So it's the APE or the average marginal effect. So the approach is the same. However, we're going to calculate the little g function for all individuals in the data. Okay. And then given that we have all the G functions for individual in the data, we're going to sum it up and then take the average. So that's why it's called the average partial effect or the average marginal effect. So basically the scale factor or the estimate of the little G function is just going to be the average of the G function at the individual level. So that's the idea of average partial or the average marginal effect. So again, for a comparison, you have the partial effects of the average, in which case you take the average of the explanatory variables in the data. Another alternative is to use the scale factor of the average marginal effect of the individuals. So these are the two estimation of the scale factor. And then again, if you're using mostly continuous variable, it doesn't really matter whether you use partial effects of the average or the average marginal effects. However, if you're using several discrete categorical variables, then it would make sense if you use the average marginal effect instead of the partial effects of the average. All right. Any questions so far related to this? Okay, great. If there is no inquiry or question, then I'm going to go to Stata, and we're going to do several, calculation using Stata. Okay, so for this particular exercise, what I want you to open is the MUS 14 data. So the MUS 14 data is a data by provided by Cameron and Trivedi's textbook, which is useful if you're interested in using Stata as your main analytical tools. And the data set is relatively big in the sense that it has several variables. So the variables that we're mostly interested in is going to be whether or not an individual has a private insurance. So ins is going to be equal to 1 if you have a private insurance, and then 0 if you do not have a private insurance. So you're interested in looking at the relationship between household income as well as the probability of using insurance. However, of course, you also want to do or add several variables of interest. Okay, so that's going to be something that we're going to do. But before we go there, let me just show you the difference between OLS and Logit and Probate. Okay, so for this comparison, I'm just going to use one particular variable, which is the household income itself. So if we do a linear probability model, it's just an OLS regression of insurance and then household income. Okay, so that's going to be the regression. Now note that in this particular example, we can see that this is the estimated coefficient on the effect of household income. Okay, so we're not going to do any interpretation first, but we're going to do some comparison on the predicted probability. So let's calculate the predicted probability of the linear probability model conditional on the estimate. We also want to do a Logit estimate on the effect of household income on whether or not an individual get insured. So as you can see here, Stata is doing some iteration. So why does it want to do some iteration? Because it wants to find the estimated coefficient such that the log likelihood is the highest. Okay, so that's why it's called the maximum likelihood. So let's give it a name. So we're going to predict here P Logit the probability. Okay, And then we're also going to do probate, and then insurance, and then household income. Okay. In this particular case, we do predict probate, and then the probability. All right. So I'm just going to do some sorting just to make sure that we have the correct graph. And now we can do the graphing. Okay. So here is 3 predicted probability lines. The green dotted line is from the predicted linear probability model. And then the black solid line as well as the blue solid line is going to be the predicted probability at the Logit and the probate respectively. So as you can see, the predicted probability under the Logit and the probate model will always be between 0 and 1. However, for the OLS, it's going to be larger than 1. So those are some of the things that we can notice. Okay, so this is just looking at the predicted probability. So what is going to be the message here? Well, the message here suggests that if you want to do a regression with a binary dependent variable model and be able to make some prediction on the probability, it's best for us to do Logit and probate instead of linear probability model. Okay. All right. So I think the next thing that we can do is do the probate regression, or you can do the Logit regression. That's fine. In this particular case, I'm just going to focus on the probate. So we have the probate of insured, and then definitely we're interested in the household income. Okay. And then we can have age, health status, whether it's a good health status, and then years of education, an indicator whether an individual is married, Hispanic, or an individual is white. And then we have female, whether or not an individual has a chronic disease, and then activities in the daily life, and then whether or not the individual is retired. Okay. So we can use the robust function as well. That's also fine. And this is the result of the probate regression. Now, again, we're looking at the estimated coefficients that maximizes the maximum likelihood function. And so that's why Stera is doing some iteration. So you want to find a combination of beta such that it maximizes the log likelihood. And so Stera is going to stop once they find that value. In many cases, they don't stop as well. So that's something that you need to pay attention to. Now, again, the estimated coefficient that we get from this regression is not particularly meaningful other than the direction. So it could be positive, it could be negative. That's the only information that is valuable at this moment. But the nominal on the estimated coefficient doesn't mean a thing. Okay. So given that we have several discrete variables, such as an indicator whether or not the individual is white, indicator on gender, an indicator on chronic, then it's more feasible for us to use the average marginal effects or the average partial effects rather than the partial effects of the average or the marginal effects of the average. The question is, how do we get the marginal effects, the average marginal effects? Well, it's relatively quite straightforward. It's just the margins, dy dx of all the explanatory variable. That's why I'm using the asterisk, and I'm just want to make it relatively simple. And so this is the result. Okay, so before I do the interpretation, I just want to highlight the difference between change in percentage and change in percentage points. Two very different things. Suppose you have two numbers, okay? You have 2% and then you have 4%. So a change from 2% to 4% is 2 percentage point. Okay. However, a change from 2% to 4% is 100%. Okay. So please distinguish between percentage point and percentage. So 2% to 4% is 2 percentage point, but it's also a change of 100%. So it really depends on what you want to use. Okay. All right. So let's in particular interpret this household income, the marginal effect of household income. So the marginal effect of household income is the following. Additional income by 1 unit, $1 in this particular case, or you can make it, an increase in income by $100. That's also fine. But every additional dollar of income is associated with higher probability of being insured privately by about 0.03 percentage point. Okay, so you have to multiply this by 100 to get the coefficient. All right. Another one is the years of education. So individuals with higher education by about a year is associated with higher likelihood of having a private insurance by about 2.57 percentage point. Okay. Another thing is being married. So individuals who are married have a higher likelihood of having a private insurance by 11.68 percentage point. Okay. Again, the interpretation is on the percentage point rather than percentage or just percent. So this is the interpretation of the marginal effects. Again, you cannot directly interpret the regression result, but instead you need to have the average marginal effects. Okay, questions? Okay, good. All right, so that's our discussion on binary dependent variable model, or the particularly on the Logit and Probate. So we did discuss about linear probability model, but given your insights on Logit and Probate, not sure why you want to use linear probability model ever again. Okay, so that's the idea, and I think we can go straight into our next discussion. So this is actually not something that I usually provide to students. However, since several students in the past are using multinomial model, so this is something that I'd like to share with everyone too. So the next discussion is on the multinomial models. Once you understand the idea between the binary dependent variable model, then it's going to be relatively straightforward to actually do the multinomial models. Okay. Why? Because the multinomial models can be interpreted as a series of binary response model. We'll see why that is the case. Okay. So we've seen this earlier in the lecture today. Many times the variable of interest are categorical data with more than 2 categories. In this case, it's also referred to as the multiple response variable. In this example, we have a categorical variable with 3 responses, whether or not individual has a national health coverage, or the BPJS Kesehatan, or the JKN, or whether individual has a private insurance or otherwise. Okay. So this is an example of a multinomial model. In this case, the choice has to be mutually exclusive. So you either have a JKN, or you have a private insurance, or you don't have either private or JKN. Okay. Another variable that is of interest is not only when you have a categorical variable, but when you have ordinal variable. Okay. So in this case, the response variable is going to represent a ranking. Okay. So whether you're happy, very happy, unhappy, and very unhappy is something that you can rank, something that is ordinal. Whether you're very satisfied, whether you're satisfied, whether you're dissatisfied, or very, very dissatisfied is also an example of a ordinal variable. Now, in this case, we're not going to use multinomial model, but we're going to use an ordered model. Now, we're not going to discuss ordered model in particular in this lecture, but once you understand the idea behind the multinomial model, it's not going to be difficult to extend your knowledge into understanding the ordered model. All right, so with any binary variable or with any multiple response model, you always want to talk about the response probability. So for each individual, the outcome Y is going to take one of the M alternative. Okay, so in this particular case, the outcome for individual I could be J equal to 1, 2, or M. So in this case, J equals to 1 is JKN, J equals to 2 is private insurance, J equals to 3 is otherwise. Okay. So the response probability right now is going to be the following. What's the probability that an individual choose alternative J conditional on observable, where the probability Y equals to J is going to be the three alternatives that we just discussed. Okay. Now, when we do the multinomial model, note that we can only specify the probabilities of M minus 1 alternative. So if you have 3 alternative, then you can only specify probability 1 and 2, and then you have to omit one of the alternative. Okay. Now the question is, why do you want to omit a variable? One, the omitted variable or the omitted alternative is going to act as the base alternative. Second, the interpretation that you will do is always going to be relative to the base alternative. So let's go back into this particular example. You have 3 categories. You have an individual with national health coverage. You have an individual with private insurance, and then you have individuals with no insurance at all. Okay. Now, in this particular case, then you can omit one of the alternative. So if you want to be strategic, you can omit no insurance at all. So later on, when you do your multinomial regression, your interpretation is always relative to the no insurance case. Okay, so it's the effect of, say, higher income on the probability of having JKN relative to having no insurance at all. What's the marginal effect of private insurance relative to no insurance at all? So that's the idea on why we want to have M minus 1 alternative. So the estimation itself is relatively straightforward. So again, first we want to identify which alternative we want to omit. And once we identify the variable that we want to omit, we're going to put it right here. And we're going to use the Logit, the variable, dependent variable of interest, and then the variables that we're interested in. Okay, so that's going to be the idea of the regression. Okay, now earlier I said that once you understand a binary response model, it's not going to be difficult to understand the multiple response model. And why that is the case? Well, it's because multinomial logit is going to be a series of pairwise logit model. So it's a logit model between having private insurance and no insurance at all. That's one logit model. And then you have another logit model between having a JKN or a universal healthcare and no insurance at all. So it's so basically it's a difference between alternative J and the base alternative. So that is why we always want to choose a base category. Now let's take a particular example that the base alternative is the first category. Okay. Now, what does beta hat J means? So as xj increases, then we're more likely to choose alternative J than alternative 1. Okay, suppose we're looking at income. So what's the effect of income on having a private insurance relative to having no insurance at all? So that's the way that we interpret it. And of course, not only that we're interested in just estimating it, we're interested in looking at the marginal effects. Again, we have two options. We have the average marginal effects. We have the marginal effects of the average. If you have continuous variable in your model, then it really doesn't make much of a difference whether you use a marginal effects of the average. Well, it's going to yield different results, but for marginal effects of the average or the average marginal effects, then it's going to be straightforward. However, if you have discrete variables, categorical variables in your model, then it would be more sensible for us to use the average marginal effects or the average partial effects. Okay, so we're going to run through an example of multinomial model. So please allow me a time just to pull up the data. Okay, all right. So in this particular case, I'm going to use the MUS15 data. Okay, so what does the data provide you? Well, we're interested in looking at the effect of price and the effect of catch rate as well as income on the type of phishing mode that they're interested in. What are the types of phishing mode that under consideration? Well, we can tabulate the mode. So you have phishing on the beach, you have phishing on the pier, you have phishing on a private boat, and you have a phishing on the charter boat mode. Okay, and so what we're interested in is looking at the relationship between the types of phishing mode and then the price, the catch rate, and the income. Okay, all right, so it's going to be relatively straightforward. The first thing that you need to do is which alternative you want to omit and becomes the base category or the base alternative. All right, we can use the beach, for example. Let's use the beach as the alternative, the base alternative. Okay, and beach is the first category. So we're going to do the Logit and then the phishing mode and then price, catch rate, income, and then we can use the robust standard error option. And we're going to set beach as the base alternative. Okay. And then we can run the regression. Since beach is the base outcome, and remember that you will not do estimation on the base alternative, then the estimation that you will get for the price create income is only for the M-1 alternative. Okay. Oh, sorry. I didn't change the screen yet. Thank you for, all right. Thank you for the notification. All right. So let me just go back a couple of steps. So again, what we're interested in is looking at the relationship, relationship between fishing mode and then the price for the chosen fishing mode, and then the catch rate, as well as the income of the individual. So in this particular case, there are 4 fishing modes: fishing on the beach, fishing on the pier, on a private boat mode, or on the charter boat mode. Okay. So the first thing that you need to do before you do a multinomial Logit estimation is to identify which is the base alternative. Okay. So the base alternative is the beach. And so you can use that for the estimation. So you can use the M-Logit mode, price, catch rate, as well as income. And then you can use the robust standard error. And then the base alternative is the first one, which is the beach. So if you look at the regression result, you won't be able to identify the estimation for the beach. Why? Because in a multinomial Logit model, you're just going to estimate M-1 alternative. Okay, since beach is already on the base, then whatever the estimated coefficient that we estimate for a particular outcome is going to be interpreted relative to the base category. Now, we cannot do the interpretation right away on the price, catch rate, and income. Why? Again, the estimate coefficient is not relatively meaningful at this point, except the the plus and minus. And so what we need to do is to do the average marginal effects. Okay, so what we can do is margins, and then dy dx. Okay, and then we want to predict, say, outcome 2. Okay, so in this particular case, we're looking at the pier. Okay, so the higher the price, then the lower the likelihood of individual choosing pier relative to the beach mode. Okay, and then the higher the catch rate, then the lower the probability of that individual is going to choose the pier relative to the base alternative, which is the beach mode. And the higher the income, the less likely the individual will choose the pier mode relative to the beach mode. Okay, and we can also do, say, the same average marginal effects for the private, for example. So here on the private, the higher the income of the individual, they're more likely to choose the private mode relative to the beach mode. Okay, and then the higher the price of getting into the private, then it's less likely for them to choose the private relative to the beach. And then if the catch rate is higher, individuals with a higher catch rate are less likely to choose the private mode relative to the beach mode. Okay, so this is going to be the interpretation of the multinomial Logit model. Okay, any questions on the multinomial Logit model? Okay, and this is since this is the last materials for the semester, I'd like to give opportunities if you have questions for materials that is delivered after the midterm, just in case you have a particular questions. And I'm going to open up a Q&A forum in Log, just in case you have questions, general questions about all the materials that are delivered after the midterm. So you can get a clearer answer on any questions or inquiries. But at the moment, if you have anything that you like to ask, please do so. All right. If there's no questions, we can end early the lecture today. After this, I'm going to set up a Q&A forum in Log so that you can ask any questions related to the materials delivered after the midterm. And again, for the final exam, we're going to use the same method. So we're going to use Log for the final exam. And the final exam date is going to follow the date set by the Faculty of Economics and Business. I guess that's the only announcement that I can make right now. Any other important announcement will be made and will be disseminated via email. All right, thank you so much for your participation during the semester. Again, I'm hoping that you learned a lot on the econometrics. And I think this is a particularly important one, particularly those who wants to focus on data analysis in the future. And even if you don't have any aspiration to do data analysis in the future, at least the rigor of the class will allow you to become a more disciplined individuals and a better individuals in the future. But for those who are interested in looking at the career path of data analysis, then this is actually a good start for you to be able to leapfrog into the future lectures. And I think we have Alexander here as well. I'd just like to congratulate Alexander and his team for the runner-up on the HSBC. I think that's a particularly prestigious competition, and it's a pride for FEB to have a winner in the competition. So I'd like to extend my congratulations for the team as well as Pa Edi Jun. All right, I think we can end the lecture earlier today. I'll see you in the next opportunities. Thank you so much. Bye-bye. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, sir.
Thank you, sir.
Thank you so much.
Thank you, sir.
Thank you, sir.
Bye.